Hi, I'm Ian Johnson, a software engineer with Wolfram Research, and my talk is about new and upcoming systems functionality in the Wolfram language. I'll be talking about operating system functionality like sockets, as well as network packet capture and other operating system programming. So this talk is going to be about systems functionality in the Wolfram language, both some new stuff that's in 11.2 that you can use, as well as some future functionality that we'll be adding in later releases. So the kind of the 11.2 stuff that you can play around with right now that I'm going to talk about is memory available and some other like system measurements that you can do with that, as well as some network programming using the new sockets functionality that we have in the Wolfram language. And then some of the future stuff that I'll be talking about relates to capturing network packets, another kind of network programming task that comes up a lot, as well as inspecting system processes, so processes running on your system that weren't started or don't really interact with Mathematica, but you can interact with those using some new functionality, as well as programmatic control of some web browsers through WebUnit. Part of the, I think, oh, okay, oh well. Anyways, okay, so the first functionality we're going to talk about, memory available. A new function we added so that you can, there's always been memory in use, which tells you how much memory is used by the Wolfram kernel, but that doesn't necessarily represent how much memory you have left in the system. So, it's sometimes useful in computations to know, okay, I have, 6 gigabytes of RAM left. If I try and load something that's larger than that, I'll fail or something else will happen. So memory available is introduced as a kind of remedy for that. So the basic function, that just returns in bytes, kind of like a best guess of what you have available. There's lots more kind of fine-grained statistics available under system information that you can view. And a lot of these are kind of like, pretty technical in terms of like what the difference is between them. And so, the physical total, that's, almost always accurate. I don't, that doesn't change. But the physical used and physical free doesn't always add up. So, for example, this machine has 16 gigabytes, but then if I subtract the, if I subtract the total minus the used, that leaves 4 gigabytes left, which should be equal to free, but it's usually not. Yeah, so there's usually a little bit of gap between some of these parameters, specifically with respect to the physical used and free. Usually it's cache memory that was used by an application that was closed and is still available if you restart that application later on. So yeah, this is kind of like a measure of how much cache memory you have available. But yeah, so memory available can also be accessed as a quantity through system information. And usually just because the time difference between when you measure it in one call and another call, sometimes there can be very small variations. So sometimes these aren't even exact, in between different calculations. But yeah, so yeah, that's kind of useful. You can make a little dynamic window here that shows you how much memory you have left, and then allocating a bunch of memory here will you'll see it dip down a little bit, and then if I clear that, it jumps right back up. So this is kind of a little cool thing that you can now implement in Mathematica, kind of inspecting that kind of memory state. Okay. So the next thing I'll talk about is with Wolfram language. So since 11.0, we've had client capability of connecting to servers and stuff using sockets. That was Socket Connect that we've always had. You can connect to wolfram.com or something. We've always had that functionality to be able to connect to another server. However, in 11.2, we added an additional socket type. We added the 0MQ socket type, which I'll talk about in a little second, and we also added the ability to open like server-side sockets. So in socket programming, that's how you make a network connection to any kind of machine, or sometimes to your same machine, is you open up socket connections, and now you can both connect to other services that are running, as well as run your own services using sockets in the Wolfram language by opening those connections up. And so the second, the same type that we've always supported is TCP, which is a stream-based protocol where it's you just kind of get data as it comes in. There's not a clear delimiter between messages. That's as opposed to the new socket type that we have, 0MQ, which is discrete message based. So what's really useful about 0MQ is that you either get the entire message or you get none of it. And so there's a lot of complication in writing these web applications a lot of times, because you don't always know if you have the full message, right? So if you're reading or writing a web page, or typically reading a response from some web server, you don't always know that you've gotten the full response yet. So you have to keep kind of polling and waiting and go through this parser state, and it's very complicated. But when you have a message-based socket like that, you either get everything you need or you get none of it. So you don't have to worry about some of that parsing state. And the other advantage of implementing 0MQ sockets is that there's a lot of different topologies supported. So TCP is always one-to-one. You have your server, and then there's the client, and they have a connection. But with 0MQ, you can start to build out these kind of more, kind of graph network type topologies, such as maybe one-to-many, where you have one server and a bunch of clients connecting to that one socket endpoint, and kind of like a distributing data like that. There's also pub-sub mechanisms where you can have multiple clients connecting to like different endpoints, and when you write a message, it can be delivered to only some of the clients and kind of control it like that. So yeah, you can have lots of different topologies available with 0MQ. So we'll just now the function to open up a socket connection to allow new connections, so like the server side aspect of a socket is socket open. So we just open that up, and when you specify this automatic parameter, that tells the operating system to just find any available open port. So in this case, it found 60,988. You can also specify, if I know there's a particular port I want to listen on, you can also specify that. Sometimes it's useful to be able to look up services, so you can specify, like the HTTP service or something like, or FTP or something like that. A lot of times, if you're not running Mathematica with sufficient permissions, you can't open sockets on ports less than like 1,000 or something like that, just due to like operating system issues. But yeah, so you can open socket connections like that, and then in the Wolfram language, you connect with just socket connect. But you can also, there are lots of other languages that have 0MQ bindings that you can connect to. So we'll just connect to the server there, and so now we have both sides of the connection. And you can use the read and write functions to write any kind of arbitrary expression on the socket connection. So here's a simple, some simple expressions, writing out. And when expressions are sent using write, they're received as two 0MQ messages. One is the full expression, and then there's a new line. So if I write this again, there's another new function that we added, which is called socket read message, which is to read a single discrete message. When you use read, that kind of expects to work with a stream, so it has all this parser state, and it'll try and figure out, okay, do I have the full expression yet? Do I need to keep waiting for more data? And it handles all that for you. But in some instances, you just want the kind of like raw, what was sent on the stream as a byte array. So you can use that with socket read message. So you can see that the first message here is a byte array is like 38 38 kilobytes, something like that. And we now have lots of, I can do byte array to string of that. That'll be some big input string. So yeah, some big graphics object with lots of stuff inside it. But yeah, so you can work with byte arrays that way. And there are also other, you can use write string and binary write, etc. If you're not writing expressions, you can kind of formulate whatever kind of protocol you want on that. So yeah, so that's 0MQ messages. So TCP sockets are usually when you have to connect to websites and stuff. You're always using TCP. So you can open up if you the default. Whoops, that shouldn't have shown up. The default message or the default type of socket is TCP because it's kind of the most common right now. And so when you open up a socket connection, typically in other programming languages, is you open up the socket and then you sit in a loop waiting for clients to connect, and then you have to accept the connection. And so it's kind of a little extra overhead that you always just have to do. And so in the Wolfram language, this is handled automatically for you. So when a client goes to connect, it is automatically handled. You don't have to, it's asynchronous in the background. You just open up the socket, and now anything can connect automatically. So now, and you access this is different than 0MQ. With TCP, because it's one-to-one, every single client that connects to your new socket that you just opened is an individual different socket connection. So you're like opening the door so that new connections can be made. And so you access those like kind of client, the other side of the client connection through this property called connected clients. So I'll just connect one. Oops. And there you go. There you can see there are two clients. I have validated it twice. So there's the two clients. So now to communicate with that particular client, you can now do individual client-based communications. Is you just do a write or write string, whatever. And then because on TCP it's a stream-based protocol, when you use socket read message specifically, it's kind of undefined how big the array that you get back, or the byte array you get back is. So here when I run this, let's see. I think I need to do the other one because now there's two clients. Yeah, there we go. Oops. Anyways, I'll just redo this. But yeah, so you can see that when you're using TCP sockets, it's hard to guarantee how big of a message that you get back on it. So yeah, so that's like kind of synchronous. You control both ends with Mathematica. Also, another really useful thing that you can do is you can do asynchronous listening and asynchronous actions such as with socket listen. So using handler functions here, we just have a simpler one where it just print something. Again, this automatic parameter says just find any open port. So we'll just connect to that to the socket that was open for us and write a message. And then if I open up the messages window, we can see that message. So there's our message that we sent, hello world, the time, that kind of thing. Oops. Got too many. Okay. So yeah, so you can that's a simple example where you're just printing off the request that you get. However, you can do a much more complicated one. That's not too much more complicated. It's just complicated in what you're sending back. Is you can generate some HTML code and send it back as a response, and now you're implementing a web server in Mathematica. So I'll just build up the URL, and if I open that in my browser window, there's our little web server that's running natively in the Wolfram language. So that's fully asynchronous. So that's pretty cool. Move this over there. So yeah. So and then with that, there's another kind of like bonus feature if you want is you can use socket listen in conjunction with local submit. Because what local submit does is it starts another new in 11.2 function, and it starts kind of a a subsession that is independent from the main kernel, that you can still interact with it and get data from that local subsession, but now you're free to use the front end and use your main kernel without getting bogged down by asynchronous requests, because currently the asynchronous requests that come in are handled the same way that like dynamics are updated. So if there's a lot of requests in your notebook that you deployed it in, that'll be pretty slowed down. So yeah, so that's all stuff that that's available to you right now. So I'm going to quick show some new stuff that we're working on. So this first function is called network packet capture, which it just takes an argument of how long to wait for, and hopefully there's something going on in the background that we get. Yeah. So here's some just a data set of what's going on. There's some encrypted this destination port of 443. That's some sort of HTTPS thing going on in the background. But a useful thing that you often want to do when you're gathering these packets is be able to filter them. So I can say specifically, only give me packets that are being sent to my machine from over HTTPS. So you can specify what port you want, and then get something back with that. So I guess there's nothing going on in the background during those 10 seconds. But there's also I don't know why that's all the way over there, but this is a very rough prototype of a GUI similar to audio capture, where you can just start capturing, select which interface you want, and then after some time, hit the stop button, and there's your data. So you can kind of do that interactive gathering of packets. And you can also use filters to do the same thing here. Probably won't get anything there, but yeah. Yeah, so there's just some code here to look at all the host names that are accessed. But more that's coming on this specifically is the ability to do this asynchronously. So if this will be useful if you're writing a function in Mathematica and you want to see what are the packets that are accessed while this function is evaluating, right? So what you can do is you'll have a network packet recording submit, which does an asynchronous task, and then you can get the result from the evaluation result. And then we'll also support importing. I don't know why it doesn't scroll all the way down. There's a bullet down there that you can't quite see. Yeah, there it is. So you'll be able to import PCAP files gathered from, say, Wireshark or something like that, and import them into Mathematica as if you had gathered them. So that's some of the new stuff. The next thing I'm going to quick show is system processes, which is for interfacing with processes in Mathematica. So currently we have run process, start process, these kind of functions for starting stuff from Mathematica. But sometimes you want to interface or control processes that weren't started from Mathematica, or at least see if they're running to see if there's services, etc. So here I just run system processes, and now I get all these process objects returned to me. Some of them, zoom in a little bit here. You can see the Wolfram kernel is somewhere. Yeah, so there's Mathematica, and you can see the parent PID and things like that, and search for specifically just ones that match that. But then another useful thing that you can do is you can actually kill these processes, assuming that you have permission. So here I'm just going to open up. Here's a notepad, simple process, and then I can kill that process. Could exit full screen, but you can kill processes sometimes, which is useful if there's something I don't know, that the system started that you need to remove. And then you can also query properties. You can get out how much memory is in use by the process as reported by the operating system. So that's slightly different than memory available, that kind of thing. How many threads are running. You can also see processes when they're running. They have like parent PIDs if they were started. So like one process A starts process B, which starts process C. Kind of a chain like that. You can look at that kind of stuff, and you can actually like build a graph of what's all running on your system. So you can see this process over here started a bunch of child processes, which kind of went into that. So it's kind of just a little cool demo thing. So yeah, then the last thing I'll show is a package that we've developed that we're going to put into the language and kind of flesh out really well, called that uses a protocol called WebDriver. And so it's programmatic control of web browser. So I have a web browser over here. And from the Wolfram language, I can open a specific page and click on things. So here I clicked on the nav bar by evaluating this click element. And then I can type there and go to that page. And I can also capture a screenshot of what that browser is doing, that kind of thing. So yeah, I think kind of went by some of the new stuff fast, but I'll stop there and open up to questions if there are any questions. Yeah, go ahead.
You mentioned about the kill process.
Yep.
Sometimes, they were talking about this yesterday, like particularly when you use parallel kernels, you can get a situation where you try to break out of it and you've got like a ghost mathematical kernel running in the background. And then next time you try to restart Mathematic, it'll tell you that it's violating the terms of your license. And you've got to,
Sure.
on the Mac, I find I have to go to the activity monitor and,
Yeah.
and manually shut that down. Is there a way to kill those ghost kernels within Mathematic?
So yes, you could. It'll be a little bit of a hack because you have to be careful not to kill the process that you're running, right? But you can get the process ID of the current running kernel, and then you could find all of the Wolfram kernels that match, that are called Wolfram kernel.exe or whatever, and then remove the one that matches your process ID, and then you could kill those other ones. I mean, it's a hack. You could run into some weird things with that. So, I have not tried. No, I have killed the process I was running in before. So, so yeah, that's probably not desirable. But yeah, there's lots of different functionality you could do with that. You could at least be able to tell, hey, are there other Wolfram kernels running? That would be something useful to be able to say. But you need a running kernel to run it. So I suppose. Yep. So with this, no, because this is just looking at what the operating system currently has. There's another functionality that Coworker is developing to remote SSH like evaluation of things. And so, if you have SSH access to that remote server, you could run SSH commands, to kill that process on a remote server from Mathematica. So that functionality would be available, but it wouldn't be directly through kill process. So, yeah. Any other questions? Yeah, go ahead.
Is this notebook posted anywhere?
So a lot of this stuff is, development stuff. So the new stuff that's in here won't be in the notebook, but the first part that's in 11.2, that'll be on Pathable a little bit later today. So you can look at the stuff that's available right now to use. Any other questions? Okay, cool. I'll be in the basement by the connected devices booth later on if you have any more individual questions. But other than that, thanks for your time.